Hello there, and welcome to the Sleepy Library. Tonight, we are wandering through the silent vastness of space itself, exploring the incomprehensible scale of the cosmos that surrounds us. The universe stretches beyond what any human mind can truly grasp, reaching outward in every direction, into distances so enormous that numbers begin to lose their meaning. Yet, within this boundless expanse, there is a strange comfort, a sense of belonging to something greater than ourselves, something ancient and patient and endlessly beautiful. If you enjoy these quiet journeys, I invite you to like, subscribe, or share a thought below. It helps others find their way here, one sleepy soul at a time. But for now, just breathe. Let the night settle around you and allow your mind to float free. Let's begin. The observable universe is approximately 93 billion light-years in diameter. To understand what this means, we must first understand what a light-year is. Light travels faster than anything else in existence, racing through the vacuum of space at 186,000 miles every single second. In just 1 second, light could circle the entire Earth more than 7 times. In 1 minute, light travels 11 million miles. Yet, even at this incredible speed, it takes light an entire year to cover the distance we call a light year, which equals about 5.88 trillion miles. When astronomers tell us the observable universe is 93 billion light-years across, they are describing a sphere of space so vast that light itself, traveling at its maximum possible speed, would need 93 billion years to cross from one edge to the other. But here is where it becomes even more interesting. The universe is only 13.8 billion years old. You might wonder how the observable universe can be wider than the age of the universe multiplied by 2. The answer lies in expansion. Space itself has been stretching outward since the beginning, carrying galaxies away from each other like raisins in rising bread dough. Objects that emitted light 13.8 billion years ago have since moved much farther away. They are now approximately 46 billion light-years from Earth in any direction, making the full diameter of what we can observe 93 billion light-years. This expansion continues today, growing at a rate that means every year the observable universe expands by 1 additional light-year in radius. Space is not just large, it is actively becoming larger, second by second, pulling the edges of what we might someday see ever farther from our view. Within this observable sphere exists everything we can detect, measure, or theoretically observe. Beyond this boundary lies more universe, perhaps infinitely more. But light from those distant regions has not had enough time to reach us since the beginning. We are surrounded by a horizon we cannot cross, not because there is an edge or wall, but because the finite speed of light and the finite age of the universe create a natural limit to what we can see. Imagine standing in an open field at night with a lantern. You can see as far as your light reaches, but beyond that circle lies darkness, not because nothing exists there, but because your light has not yet arrived. The observable universe is our cosmic lantern light, illuminating a sphere that grows slowly larger with each passing moment. The universe contains an estimated 2 trillion galaxies. Early observations suggested there might be 100 to 200 billion galaxies scattered throughout observable space. But improved measurements and deeper imaging have revealed a far more crowded cosmos. Many of these galaxies are small and faint, too dim to be seen with current technology. but mathematical models predict their existence based on what we can observe. Some of these tiny galaxies contain only a few million stars, while others stretch across hundreds of thousands of light-years and hold trillions of suns. Each galaxy is a vast island of light in an ocean of darkness, separated from its neighbors by millions or billions of light-years of mostly empty space. If you were to pick a random point anywhere in the observable universe, the chances are overwhelming that you would land in empty space, not near a star or planet or galaxy. Most of the universe is void, yet within those scattered islands of matter, the diversity is staggering. Spiral galaxies spin gracefully, with arms of stars and dust trailing behind like cosmic pinwheels. Elliptical galaxies glow softly as ancient spheres of old stars, having long ago exhausted their supplies of gas needed to birth new ones. Irregular galaxies tumble through space in chaotic shapes, often the result of collisions or gravitational encounters with neighbors. Some galaxies are so massive they contain more than 100 trillion stars. Others are so small and sparse they hover on the edge of what we might even call a galaxy at all. The observable universe contains approximately 1 septillion stars. That is a 1 followed by 24 zeros. Written out, it looks like this: 1 million trillion trillion. To put this in perspective, there are more stars in the observable universe than there are grains of sand on all the beaches of Earth combined. Each of those stars is a sun, potentially surrounded by planets, moons, asteroids, and comets. Each one generates light and heat, fusing hydrogen into helium in its core and releasing energy that travels outward into space. Some stars are small and cool, glowing dim red and burning their fuel so slowly they may shine for trillions of years, longer than the universe has yet existed. Others are massive and brilliant, burning through their reserves in just a few million years before collapsing or exploding in brilliant supernovae. Our own Milky Way galaxy, the cosmic home we inhabit, contains between 200 billion and 400 billion stars. It stretches about 100,000 light-years from edge to edge, a spiral of starlight slowly rotating through space. Our Sun sits about 26,000 light-years from the galactic center, in a quiet region between major spiral arms. If you could see the Milky Way from the outside, it would appear as a luminous disk with a bright central bulge, spiral arms winding outward through regions of blue young stars and pink nebulae, where new stars are being born. From our vantage point inside, we see the disk edge on as a band of light stretching across the night sky, a river of distant suns blending together into a soft glow. Yet, for all its grandeur, the Milky Way is not especially large. The Andromeda Galaxy, our nearest major neighbor, spans approximately 220,000 light-years across and contains roughly 1 trillion stars. It lies 2.5 million light-years from us, close enough that on a dark night it appears as a faint smudge of light visible to the unaided eye. Light that reaches your eyes tonight from Andromeda left that galaxy 2.5 million years ago, when early humans were just beginning to walk upright on the plains of Africa. You are seeing ancient light, a message from the past carried across the void at the speed of the cosmos itself. Beyond our local neighborhood, galaxies exist in even more spectacular forms. The galaxy IC 1101, one of the largest known galaxies, stretches up to 4 million light-years in diameter. It is a supergiant elliptical galaxy located over 1 billion light-years away, so massive that it dwarfs the Milky Way by a factor of 40. If you were to replace the Milky Way with IC 1101, the Andromeda Galaxy would fit comfortably inside it, along with dozens of other galaxies like ours. Such colossal galaxies typically sit at the centers of galaxy clusters, their enormous gravity wells pulling in smaller galaxies over billions of years, growing larger with each merger. The distances between galaxies are themselves almost beyond comprehension. From Earth to the Andromeda Galaxy is 2.5 million light-years. If you could somehow travel at the speed of light, the journey would take 2.5 million years. If you traveled at the speed of a commercial airplane, about 600 miles per hour, the trip would take approximately 4.4 billion years. If you walked at a leisurely pace of 3 miles per hour, it would take 880 billion years, more than 60 times the current age of the universe. These distances are not barriers placed by physics or technology. They are simply the way space is, vast and patient, indifferent to our desire to cross it quickly. Our local group of galaxies, the gravitational family that includes the Milky Way and Andromeda, along with about 80 other smaller galaxies, spans roughly 10 million light-years across. Beyond this, the local group is part of a larger structure called the Virgo supercluster, which contains thousands of galaxies and stretches about 110 million light-years in diameter. But even this is merely one small part of an even larger structure called the Laniakea supercluster, a collection of superclusters that includes our Virgo supercluster and spans 520 million light-years. Within this vast cosmic web, galaxies are not distributed evenly, but cluster along vast filaments, creating a foam-like structure with immense voids between. If you could step back and see the entire observable universe at once, it would resemble a cosmic spiderweb, with glowing strands of galaxies crisscrossing through vast empty regions of space. Each point of light in the night sky that we call a star is actually a sun, many of them much larger than our own. Our sun is a medium-sized star, about 865,000 miles in diameter. It contains 99.86% of all the mass in our solar system. Everything else, all the planets, moons, asteroids, comets, and dust combined, makes up less than 1/5 of 1% of the total. Yet compared to other stars, our sun is unremarkable. Some stars are tiny red dwarfs, barely larger than the planet Jupiter, glowing faintly in the infrared. Others are blue hypergiants, stars so enormous they would swallow Jupiter's orbit if placed where our sun sits. One such star, VY Canis Majoris, has a radius about 1,500 times that of our sun. If you replace the sun with VY Canis Majoris, its outer layers would extend beyond the orbit of Saturn. Stars are born in vast clouds of gas and dust, called molecular clouds, regions that can span hundreds of light-years and contain enough material to birth thousands or even millions of stars. When gravity causes these clouds to collapse, pockets of gas heat up until nuclear fusion ignites in their cores, and a new star begins to shine. The leftover material often forms a disk around the young star, and within this disk, planets may gradually coalesce. Around many stars, astronomers have detected planets, some rocky like Earth, others gaseous like Jupiter, and some utterly unlike anything in our solar system. Current estimates suggest that nearly every star in our galaxy hosts at least one planet, and many have multiple worlds orbiting them. This means there could be hundreds of billions of planets in the Milky Way alone, and trillions upon trillions throughout the observable universe. The scale of our solar system itself is difficult to grasp. We think of Earth as distant from the Sun, separated by 93 million miles, a distance we call 1 astronomical unit. Light from the Sun takes 8 minutes and 20 seconds to reach us, which means we always see the Sun as it was slightly over 8 minutes ago. If the sun were to suddenly vanish, we would not know for 8 minutes, continuing to see its light and feel its warmth until that final photon completed its journey. Neptune, the most distant planet, orbits about 30 times farther from the Sun than Earth does, at approximately 2.8 billion miles. Light from the Sun takes about 4 hours to reach Neptune. But even Neptune is not the edge of the solar system. Beyond Neptune lies the Kuiper Belt, a region of icy bodies that includes Pluto and extends to about 50 astronomical units from the Sun. Farther still is the scattered disk, and beyond that, at the outermost reaches of the Sun's gravitational influence, lies the Oort cloud, a vast spherical shell of comets that may extend halfway to the nearest star. The Oort cloud is thought to reach as far as 100,000 astronomical units from the Sun, or nearly 2 light-years. If you were standing at the outer edge of the Oort cloud, the Sun would appear as just another star in the sky, not noticeably brighter than the others. Our solar system is enormous, yet it occupies only a tiny fraction of the distance to the next nearest star. That nearest star is Proxima Centauri, a small red dwarf located 4.24 light-years from Earth. This is approximately 25 trillion miles, or about 268,000 times the distance from Earth to the Sun. If we built a scale model where the Earth was the size of a grain of sand, about 0.004 inches across, the distance to Proxima Centauri would be nearly 1,000 miles. If we shrunk the entire solar system down to the size of a quarter, Proxima Centauri would still be more than 2 football fields away. The fastest spacecraft ever built, NASA's Parker Solar Probe, reaches speeds of about 430,000 miles per hour as it approaches the Sun. At that speed, it would still take over 6,000 years to reach Proxima Centauri. Yet Proxima Centauri is our very closest neighbor. The next nearest stars are slightly farther, and then farther still, and the distances quickly become overwhelming. The Milky Way galaxy contains hundreds of billions of stars, and the average distance between them is about 5 light-years. Some regions are more crowded, with stars packed more closely together, while others are sparse and lonely. In the dense core of the galaxy, stars may be separated by only a few light months, or even light weeks, close enough that their gravitational influence on one another becomes significant. In the outer reaches, where our Sun resides, stars are more widely spaced, each island of light surrounded by vast emptiness. If you could travel at the speed of light, crossing the Milky Way from one edge to the other would take 100,000 years. At the speed of our fastest spacecraft, the journey would require over 1 billion years. Walking at 3 miles per hour, it would take more than 200 trillion years, far longer than the universe has existed or likely ever will exist. These timescales are so long that they lose connection to anything we experience in daily life. They become abstract, mathematical, a way of describing distances that no human will ever traverse. And yet the Milky Way is just one galaxy among trillions. If the Milky Way were reduced to the size of a coin, the observable universe would still be thousands of miles across. The distances between galaxies are even more staggering than the distances between stars. The Andromeda Galaxy is 2.5 million light-years away, but many galaxies are billions of light-years distant. Some of the most distant galaxies ever observed are more than 13 billion light-years from Earth. We see them as they appeared when the universe was very young, less than 1 billion years old. The light we detect from these galaxies began its journey across space long before Earth even existed, traveling for over 90% of the universe's total age before finally arriving at our telescopes. When we look out into space, we are also looking back in time. Light takes time to travel, and the farther away an object is, the older the light we see. When you look at the moon, you see it as it was 1.3 seconds ago. When you look at the sun, you see it as it was 8 minutes ago. When you look at stars in the night sky, you see them as they were years, decades, or centuries ago, depending on their distance. Some of the stars you see may no longer exist, their light still traveling across space long after the star itself has finished its life. When we observe distant galaxies, we are witnessing the universe as it was billions of years ago, a cosmic fossil record written in light. The most distant thing we can observe is the cosmic microwave background, a faint glow of radiation that fills all of space. This light was emitted approximately 380,000 years after the Big Bang, when the universe cooled enough for atoms to form and light to travel freely for the first time. The matter that emitted this ancient light has since moved much farther away due to the expansion of space, and is now calculated to be about 46 billion light-years from Earth. This radiation provides a snapshot of the universe in its infancy, a time before stars or galaxies existed, when everything was hot and dense and glowing with thermal energy. Observing it is like looking at baby pictures of the cosmos itself. The universe may be infinite in extent. The observable universe is finite, limited by the speed of light and the age of the universe. But this does not mean the universe as a whole has an edge or boundary. Many cosmologists believe that space continues beyond what we can see, possibly forever. If the universe is infinite, then it contains an infinite number of galaxies, an infinite number of stars, and an infinite number of worlds. This is difficult to imagine, but no more so than any other aspect of the cosmic scale. The universe we can observe is already so large that adding more, even infinitely more, does not change the fundamental challenge of comprehending its size. Even the observable universe is mostly empty. If you were to take all the matter in the universe, every star, planet, gas cloud, and speck of dust, and spread it evenly throughout the entire observable volume, you would have about 5 hydrogen atoms per cubic meter. That is an emptiness almost beyond comprehension. The universe is not crowded, it is profoundly, overwhelmingly vacant. The distances between objects are so vast, and the objects themselves so tiny in comparison, that collisions and encounters are rare. Galaxies can pass through one another, their stars so widely spaced that no actual impacts occur. Light crosses these voids for billions of years without encountering anything at all. And yet, within this emptiness, complexity and beauty flourish. Stars ignite, planets form, and on at least one world, life has emerged to contemplate the vastness that surrounds it. We exist in a tiny, improbable corner of an unimaginably large universe, and yet we are part of it. Every atom in our bodies was forged in the heart of a star that lived and perished billions of years ago. We are made of stardust, the remnants of ancient suns scattered into space and eventually gathered into new worlds. The calcium in our bones, the iron in our cells, the oxygen we breathe, all were created in stellar furnaces and dispersed across the cosmos before finding their way into us. We are not separate from the universe. We are expressions of it, temporary arrangements of matter that have somehow become aware of themselves and their surroundings. To put the scale of the universe in more tangible terms, imagine if Earth were the size of a grain of sand, roughly the size of the period at the end of a sentence. On this scale, the Sun would be about the size of a small marble located 19 feet away. Jupiter would be a peppercorn orbiting about 100 feet from the marble Sun. Neptune would orbit at 600 feet away, and the edge of the solar system, the Oort cloud, would extend outward to nearly 40 miles. Yet, even at this scale, the nearest star would still be 1,000 miles away, and the Milky Way galaxy would stretch 46 million miles across. The observable universe, at this scale, would measure roughly 37 million kilometers in diameter, still too large to fit in your imagination. If, instead, we shrink the entire solar system down to the size of a grain of sand, the Milky Way galaxy becomes about the size of North America. At this scale, the Andromeda galaxy would be about the size of the United States, located roughly 10 inches away from our Milky Way grain. The entire observable universe would still be enormous, stretching for hundreds of meters in all directions. No matter how we scale the cosmos, it refuses to become small or comprehensible. It remains vast, stretching always beyond the limits of our intuition. Consider this. If you could count one star per second, it would take you 31,000 years to count 1 trillion stars. To count all the stars in the observable universe at 1 per second would require 30 million trillion years, more than 2 quintillion times the current age of the universe. If you devoted every waking moment of an average human lifetime to counting, and somehow managed to count 100 stars per second without pause, you would still not reach even a tiny fraction of the total before your time ran out. The numbers are too large to be grasped by experience. We can write them, calculate with them, and use them to describe the universe, but we cannot truly feel their magnitude. The space between galaxies is not entirely empty, but filled with an incredibly thin gas called the intergalactic medium. This gas has an average density of less than 1 atom per cubic meter, making it far more rarefied than any vacuum we can create on Earth. Yet, over the vast scales of intergalactic space, even this tenuous material adds up to significant mass. Between galaxy clusters, the gas is even thinner, and in the largest voids, vast regions of space, hundreds of millions of light-years across, there is almost nothing at all. These voids are the emptiest places in the universe, containing only occasional small galaxies and faint wisps of gas. Spaces where a traveler could journey for tens of millions of light-years in any direction without encountering a single large galaxy. Galaxies do not sit still. They move through space, pulled by gravity toward large concentrations of mass. Our Milky Way and the Andromeda galaxy are moving toward each other at about 250,000 miles per hour. In about 4 billion years, they will collide, their stars passing through one another like 2 clouds of gnats interpenetrating. Very few stars will actually hit each other because the distances between them are so large. But the gravitational interaction will disrupt both galaxies, pulling out long streams of stars and gas, eventually causing the 2 galaxies to merge into a single, larger elliptical galaxy. This process is happening throughout the universe, galaxies colliding and merging over timescales of billions of years, slowly building larger and larger structures. Our solar system is also in motion. We orbit the center of the Milky Way at a speed of about 500,000 miles per hour, taking roughly 230 million years to complete one full orbit. In the time since dinosaurs walked the Earth, our solar system has traveled only about 1/3 of the way around the galaxy. Since the Sun formed 4.6 billion years ago, it has completed only about 20 orbits. The galaxy itself is moving as well, pulled by the gravity of nearby galaxy clusters. Everything in the universe is in motion, swirling and flowing through space, galaxies orbiting within clusters, clusters moving through superclusters, all of it slowly evolving and rearranging over cosmic timescales. Light itself, though the fastest thing in the universe, travels slowly when measured against cosmic distances. A beam of light could circle the Earth 7 times in 1 second, but it takes over 4 years to reach the nearest star, 100,000 years to cross the Milky Way, and 2.5 million years to reach Andromeda. The most distant galaxies we can observe are so far away that their light has been traveling toward us for over 13 billion years, covering a distance so vast that if you could freeze the universe in place and measure from here to there, the distance would be far greater than 13 billion light-years due to the expansion of space itself during the light's journey. The universe continues to expand, and that expansion is accelerating. Distant galaxies are moving away from us faster and faster, driven by a mysterious force called dark energy that pervades all of space. This acceleration means that there is a limit to what we will ever be able to see. Galaxies beyond a certain distance are receding faster than light can travel, and we will never be able to observe them, no matter how long we wait. As time goes on, more and more galaxies will cross this boundary and fade from view, eventually leaving only our local group of galaxies visible in the night sky. Billions of years in the future, astronomers in distant galaxies might look out and see an apparently empty universe, with no other galaxies visible at all, unaware that they are part of a much larger cosmos that has simply expanded beyond their ability to observe. The observable universe is shaped like a sphere, with Earth at the center. This is not because Earth is actually at the center of the universe, but because we can only see light that has had time to reach us since the Big Bang. An observer on another planet in a distant galaxy would see their own observable universe, a different sphere centered on their location. Our observable universes would overlap, but each would include some regions the other could not see. In this sense, every location in the universe is the center of its own observable sphere, and no place is more central than any other. The universe has no preferred location, no special point from which everything expands. Instead, every point sees all other points moving away, as though it were the center, a consequence of space itself expanding everywhere at once. One way to think about cosmic expansion is to imagine a balloon being inflated. Dots drawn on the surface of the balloon represent galaxies. As the balloon expands, every dot moves away from every other dot, and each dot could think of itself as stationary, with all the others moving away. None of the dots is actually at the center of the expansion, because the center of the balloon is inside the balloon, not on its surface. Similarly, the universe expands in a way that does not require a center within the space we inhabit. Space itself is stretching, carrying galaxies along with it, and there is no edge or boundary to this expansion, at least none that we have detected. The universe is also incredibly old. 13.8 billion years is a timescale almost as difficult to grasp as the vast distances. If you compressed the entire history of the universe into a single year, with the Big Bang occurring at midnight on January 1st, the Milky Way galaxy would not form until about March. The Sun and Earth would not appear until early September. Complex life on Earth would not arise until mid-December. Dinosaurs would walk the Earth for a few hours on December 30th before vanishing in an extinction event. Modern humans would appear in the final minutes before midnight on December 31st. All of recorded human history would occur in the last few seconds of the year. The universe has been around for an almost incomprehensible length of time, and the story of humanity occupies only the tiniest sliver at the end. During those 13.8 billion years, countless stars have been born, lived, and perished. Some stars that formed in the early universe are still shining today. Ancient red dwarfs that burn their fuel so slowly they may continue for trillions of years more. Others have long since exhausted their fuel and collapsed into white dwarfs, neutron stars, or black holes. The heavy elements that make up planets and life were created inside stars and scattered into space when those stars reached the end of their lives. The first stars contained almost no heavy elements at all, composed almost entirely of hydrogen and helium left over from the Big Bang. Only after several generations of stars had lived and perished did the universe become enriched with carbon, oxygen, iron, and all the other elements necessary for planets and life. We exist because stars before us lived and passed away, seeding the cosmos with the building blocks of everything we see around us. Black holes, some of the strangest objects in the universe, represent another aspect of cosmic scale. Supermassive black holes reside at the centers of most large galaxies, including our own. The black hole at the center of the Milky Way, called Sagittarius A star, contains about 4 million times the mass of the Sun, compressed into a region smaller than the orbit of Mercury. Some supermassive black holes are billions of times more massive than the Sun. The black hole at the center of the galaxy, Messier 87, weighs about 6.5 billion solar masses and has an event horizon, the point of no return, with a diameter of about 24 billion miles. This is larger than our entire solar system out to the orbit of Neptune, all occupied by a region of space so warped by gravity that not even light can escape once it crosses the boundary. Despite their name, black holes are not empty. They contain matter compressed to such extreme density that a teaspoon of material from the center of a black hole might weigh as much as a mountain. Around supermassive black holes, matter often forms a swirling accretion disk, spiraling inward and heating to millions of degrees before disappearing across the event horizon. These disks shine brilliantly, sometimes outshining the entire galaxy that surrounds them. Jets of particles and energy can blast out from near the black hole's poles, shooting across space at nearly the speed of light and extending for hundreds of thousands of light years. These jets are powered by the immense gravitational and magnetic forces near the black hole, and they are some of the most energetic phenomena in the universe. There are cosmic structures even larger than galaxies. Galaxy clusters can contain thousands of galaxies bound together by gravity, spanning tens of millions of light years. Superclusters, collections of galaxy clusters, can stretch for hundreds of millions of light years. These structures are not random. They trace out a cosmic web, with galaxies and clusters lying along vast filaments of dark matter, the invisible substance that makes up most of the matter in the universe. Dark matter does not emit or absorb light, so we cannot see it directly, but we can detect its presence through its gravitational effects on visible matter. Without dark matter, galaxies would not have formed, and the universe would be a much simpler and emptier place. Dark energy is even more mysterious than dark matter. It makes up about 68% of the total energy content of the universe, yet we do not know what it is. We know it exists because its effects can be measured in the accelerating expansion of space, but its nature remains one of the greatest unsolved puzzles in physics. Dark matter, dark energy, and ordinary matter together make up the entire cosmos, and yet we understand only the smallest component, the ordinary matter that makes up stars, planets, and us. The universe is not only vast in space and time, but also in mystery. filled with phenomena we are only beginning to comprehend. Consider the sheer number of worlds that might exist. If each star has on average one planet, and there are 1 septillion stars in the observable universe, then there might be 1 septillion planets as well. Many of these planets will be inhospitable, too hot or too cold, lacking atmospheres or solid surfaces. But even if only a tiny fraction are Earth-like, the number of potentially habitable worlds becomes staggering. If 1 in a million planets could support life, that would still be 1 quintillion Earth-like worlds scattered throughout the observable universe. Even if intelligent life is extraordinarily rare, arising on only 1 in a billion habitable planets, there could still be 1 trillion civilizations out there, each looking up at their own night sky and wondering if they are alone. Yet the distances are so vast that communication between civilizations, even if they exist, may be impossible. A radio signal sent to a planet 1,000 light-years away would take 1,000 years to arrive. If someone responded immediately, their answer would not reach us for another 1,000 years. A conversation would require millennia between exchanges. For planets tens of thousands or millions of light-years away, communication becomes meaningless on any human timescale. We are isolated by distance, each world an island in the cosmic sea, separated by gulfs of space too wide to cross with current technology, or any technology we can currently imagine. This isolation gives a special poignancy to our existence. Here we are, on this small world orbiting an unremarkable star in a quiet region of an ordinary galaxy. 1 planet among trillions upon trillions, aware of the vastness that surrounds us, but unable to reach more than the tiniest fraction of it. We have sent spacecraft to the edge of our solar system, but even the nearest star is thousands of times farther. We have looked deep into space with telescopes, seeing galaxies billions of light-years away. But we will never visit them. They exist only as images, ancient light captured by sensors and turned into pictures. Ghosts of distant places frozen in time. And yet, in another sense, we are connected to all of it. The atoms in our bodies came from stars. The light that warms our planet comes from the sun, itself a star like billions of others. The forces that govern the falling of an apple are the same forces that hold galaxies together. The laws of physics are the same everywhere, from the smallest particle to the largest cosmic structure. We are not outside the universe looking in. We are part of it, made of the same matter, governed by the same rules, existing within the same vast and ancient space. The universe is not just something we observe, it is what we are. To exist at all is an improbable thing. The universe could have been lifeless, a cold expanse of hydrogen and helium with no stars, no planets, no complexity. The laws of physics could have been different, producing a universe where matter never clumped into galaxies, or where stars burned out too quickly for planets to form. But instead, we have this universe, one where matter gathers and organizes, where stars shine for billions of years, where planets form and occasionally become cradles for life. Against the odds, complexity emerged from simplicity. Order arose from chaos. Consciousness awakened within matter, and the universe became aware of itself. The size of the universe invites contemplation. It reminds us that we are small, not in a diminishing way, but in a way that puts our concerns into perspective. The worries and troubles that occupy our minds are real and important to us, but they are also temporary and local. The universe is vast and ancient, and will continue long after we are gone. This can be humbling. but it can also be freeing. There is a comfort in knowing that the cosmos does not depend on us, that it existed long before we arrived and will exist long after we depart. We are guests here, brief visitors in an ancient and enormous theatre, witnessing a play that has been running for billions of years and will continue for billions more. At the same time, the universe's vastness makes the fact of our existence all the more remarkable. We are tiny, yes, but we are also aware. We can look up at the stars and understand, at least in part, what we are seeing. We can measure the distances, calculate the ages, and trace the history of the cosmos from the Big Bang to the present moment. We can build telescopes that peer across billions of light years, and instruments that detect the faint whisper of radiation from the early universe. We are small, but we are not insignificant. We are the universe's way of knowing itself, fragments of stardust that have somehow learned to wonder. There is a certain peace in contemplating these vast scales. The universe is so large that our individual struggles, while important to us, are not important to the cosmos. This is not nihilism, but perspective. It means that mistakes can be forgiven, that embarrassments will fade, that the things that keep us awake at night are not permanent or all-encompassing. The universe has room for countless worlds, endless possibilities, and infinite patience. We do not need to carry the weight of existence on our shoulders. We are part of something much larger, and that larger thing will take care of itself, regardless of what we do or fail to do. Imagine floating in space, far from any star or galaxy, surrounded by darkness in every direction. The nearest light might be millions or billions of light years away, too faint and distant to see with unaided eyes. You would be alone, in a way that is difficult to comprehend, surrounded by emptiness that stretches farther than light can travel in a human lifetime. And yet, even there, you would still be part of the universe. You would still be made of matter created in ancient stars. You would still be governed by the same forces that shape galaxies and bend light. Isolation in space is not the same as being cut off from existence. You are always part of the whole, always connected by the fundamental fabric of reality itself. The expansion of the universe means that the farthest galaxies are moving away from us at speeds greater than the speed of light. This does not violate relativity, which says nothing can move through space faster than light, because the galaxies are not moving through space. Instead, space itself is expanding, carrying the galaxies along with it. From our perspective, distant galaxies appear to be rushing away, their light stretched to longer wavelengths by the expansion, shifting from visible colors toward the infrared and eventually becoming undetectable. This redshift tells us how fast the universe is expanding and allows us to calculate distances to the most remote galaxies. It is a cosmic Doppler effect, the universe itself stretching the light waves as they travel across billions of light years of expanding space. One day, far in the future, the expansion of the universe may carry nearly all galaxies beyond our observable horizon. Only the galaxies in our local group, bound together by gravity too strong for expansion to overcome, will remain visible. The night sky will grow darker as distant galaxies fade from view, their light stretched and redshifted until it becomes undetectable. Eventually, an observer in that distant future might look up and see only a handful of nearby galaxies, unaware that they are part of a much larger universe that has simply expanded beyond the reach of observation. The cosmos will still exist, vast and full of galaxies, but it will be invisible, hidden behind an ever-growing horizon. But that is billions of years away. A future so distant it is difficult to imagine. For now, the universe is full of light. Every night, when we look up, we see stars and galaxies scattered across the sky, their light reaching us after journeys that sometimes span billions of years. Each photon that enters our eyes is a messenger from the past, a tiny packet of energy that has traveled across unimaginable distances to bring us information about distant places and times. When we study the cosmos, we are not just learning about what is out there, we are learning about where we came from, how the universe evolved, and what our place is within it. The size of the universe also raises questions about what lies beyond. If the observable universe is 93 billion light-years across, what is beyond that boundary? Is there more universe stretching infinitely in all directions? Or is there some kind of edge or boundary, a place where space itself ends? Most cosmologists believe the universe continues beyond what we can see, possibly forever. There is no reason to think that the part we can observe is special or unique. More likely, it is just a small sample of a much larger whole, and what lies beyond the horizon is more of the same. More galaxies, more stars, more planets, extending without end into the infinite. Or perhaps the universe is finite but unbounded, like the surface of a sphere. A traveler on a sphere can move in any direction and never reach an edge, eventually returning to their starting point after circling the globe. Similarly, the universe might curve back on itself in some higher dimensional sense, so that traveling far enough in one direction would eventually bring you back to where you started. This is difficult to visualize, but it is mathematically consistent with what we observe. If the universe is shaped this way, it could be finite in volume, but still have no boundary or edge. We simply do not yet know. The universe may be infinite, or it may be vast but finite. Either way, it is far larger than anything we will ever be able to explore. Some theories suggest that our universe might be one among many, part of a multiverse where countless other universes exist beyond our own. Each universe might have different physical laws, different constants of nature, different outcomes for how matter and energy behave. Most of these universes might be lifeless, their laws of physics preventing the formation of stars or galaxies. But in a few, conditions might be just right for complexity and life to arise. We would naturally find ourselves in one of those rare, life-supporting universes, simply because we could not exist in any of the others. This idea is speculative, with no direct evidence to support it, but it offers one possible explanation for why our universe seems so finely tuned to allow the existence of stars, planets, and life. Whether or not other universes exist, our own universe is more than enough to occupy our thoughts. It is vast, ancient, beautiful, and full of mysteries. We have learned so much about it in the last century, from the discovery of galaxies beyond the Milky Way, to the detection of the cosmic microwave background, to the realization that the universe is expanding and accelerating. We have measured the age of the cosmos, counted the galaxies, and traced the history of the universe from the Big Bang to the present. Yet for all we have learned, there is far more we do not yet understand. Dark matter and dark energy remain mysteries. The formation of the first stars and galaxies is still being pieced together. The ultimate fate of the universe, whether it will expand forever or eventually collapse back on itself, is uncertain. These unknowns are part of what makes the universe so compelling. It is not a finished story, but an ongoing investigation, a puzzle with pieces still being discovered and fitted together. Every answer raises new questions. Every observation opens new avenues of inquiry. The universe is not a static thing to be catalogued and filed away. It is dynamic, evolving, full of surprises. Each new telescope, each new instrument, each new mission brings the possibility of discovering something unexpected, something that changes how we think about the cosmos and our place within it. There is something deeply soothing about the night sky. Looking up at the stars, we connect with something timeless and universal. The same stars that shine down on us tonight shone on our ancestors thousands of years ago, and they will shine on our descendants thousands of years hence. The patterns of the constellations, though slowly shifting over millennia due to the proper motion of stars, remain recognizable across human history. The Milky Way stretches overhead, as it has for as long as humans have looked up, a river of light that every culture has noticed and wondered about. We are part of a long chain of observers, each generation looking up and asking the same questions. Where did we come from? What is out there? Are we alone? We do not yet have complete answers to these questions, but we are closer than any previous generation. We know that we are made of stardust, that the universe is 13.8 billion years old, that it contains trillions of galaxies, each with billions of stars. We know that planets are common, that many orbit in the habitable zones of their stars, that the ingredients for life are abundant throughout the cosmos. We do not yet know if life exists elsewhere, but the vastness of the universe suggests that it might. With so many stars and so many planets, it would be surprising if Earth were the only world to host life. Somewhere out there, on a planet orbiting a distant star, there might be other beings looking up at their own night sky and wondering the same things we wonder. But even if we are alone, that does not diminish the value of our existence. It might even enhance it, making us not just observers of the universe, but the universe's only observers, the only part of the cosmos that has become aware of itself. In that case, we would carry a special responsibility to understand, to preserve, to wonder. We would be the universe's consciousness, its way of experiencing itself from the inside. Whether or not we are alone, we are part of something ancient and vast and astonishingly beautiful. The silence of space is profound. In the vacuum between stars, there is no air to carry sound, no medium for vibrations to propagate. Even the most violent events, the explosion of a supernova or the collision of black holes, occur in total silence. We cannot hear the universe, only see it. And even then, we see only the light that has managed to reach us across the vast distances. Most of what happens in the cosmos occurs in darkness and silence, unobserved and unknown. Stars are born and perish in distant galaxies. Planets form and are destroyed. Black holes consume matter and emit jets of energy, all without witness. The universe does not need an audience. It simply is, existing and evolving according to the laws of physics, indifferent to whether anyone is watching. Within this vast cosmos, there are structures that challenge even our expanded sense of scale. The largest known structure in the observable universe is the Hercules Corona Borealis Great Wall, a collection of galaxy clusters that spans approximately 10 billion light-years. To put this in perspective, this single structure is more than 1/10 the diameter of the entire observable universe. If you could somehow travel at the speed of light, it would take 10 billion years just to cross from one end to the other. The structure is so large that it challenges our understanding of how the universe evolved, because conventional theories suggest that structures this massive should not have had enough time to form in the age of the universe available. The cosmic web that galaxies trace out across space follows the distribution of dark matter, the invisible substance that makes up about 27% of the universe's total mass and energy. Dark matter does not interact with light, so we cannot see it directly, but its gravitational effects are unmistakable. Without dark matter, galaxies would not have enough mass to hold themselves together. They would spin so fast that stars would fly off into space. galaxy clusters would not stay clustered. The universe as we see it simply would not exist without this invisible component. Computer simulations that include dark matter produce virtual universes that look remarkably like our own, with galaxies clustering along filaments and vast voids in between. Simulations without dark matter produce universes that look nothing like what we observe. Between the massive filaments of galaxies lie cosmic voids, vast regions of space that contain very few galaxies. These voids can be hundreds of millions of light-years across, nearly empty expanses where a traveler might journey for immense distances without encountering a single major galaxy. The Bootes void, discovered in the late 20th century, spans approximately 330 million light-years in diameter and contains only about 60 galaxies, where a typical region of space that size might contain several thousand. Standing in the center of such a void, an observer would see almost no galaxies in any direction, just empty darkness stretching for hundreds of millions of light-years before reaching the nearest filaments of the cosmic web. These voids are not truly empty. They contain dark matter spread thinly throughout their volumes. They also contain some of the intergalactic medium, gas so diffuse that there might be only one atom in every few cubic meters of space. But compared to the dense regions where galaxies cluster, voids are remarkably vacant. They represent the largest known structures in the universe, defined not by what they contain, but by what they lack. In a sense, the universe is more void than anything else. The galaxies, for all their numbers and brilliance, occupy only a small fraction of the total volume of space. Most of the universe is empty, or nearly so, vast stretches of darkness punctuated by occasional islands of light. The concept of infinity becomes relevant when we consider the universe beyond what we can observe. If space extends infinitely in all directions, then it contains an infinite number of galaxies, an infinite number of stars, and an infinite number of planets. This is difficult to grasp because infinity is not just a very large number. It is fundamentally different from any finite quantity, no matter how enormous. In an infinite universe, every possible arrangement of matter that does not violate the laws of physics must occur somewhere. There would be infinite planets, exactly like Earth. Infinite copies of every person who has ever lived. Infinite variations on every possible theme. This raises strange philosophical questions about identity and uniqueness. But it is a natural consequence of infinite space combined with finite building blocks. Some cosmologists argue that the universe is more likely to be finite but unbounded, shaped in some higher dimensional way that allows it to close back on itself without having an edge. The analogy often given is the surface of a sphere. An ant walking on a basketball can travel in any direction and never reach an edge, eventually returning to its starting point after circling the ball. The ant might think its two-dimensional surface is infinite, but it is actually finite, just curved in a third dimension that the ant cannot perceive. Similarly, our three-dimensional space might be curved in a fourth spatial dimension we cannot see, creating a universe that is finite in volume but has no boundary or edge. If this is the case, a spaceship traveling in one direction for long enough would eventually return to its starting point, having circumnavigated the entire universe. Current measurements suggest that if the universe is curved, the curvature is extremely slight. Space appears to be very nearly flat, at least within the observable region. This means that if the universe does curve back on itself, it must be vastly larger than the part we can see. The observable universe would be just a tiny patch on an enormous cosmic sphere, too small to detect the overall curvature. It is like trying to measure the curvature of the Earth by examining a small tile on the floor. Unless the measurements are extraordinarily precise, the tile appears flat, even though it sits on a spherical planet. Similarly, our observable universe appears flat, even though it might be part of a much larger, curved structure. The speed of light sets a fundamental limit on how quickly information can travel through the universe. At 186,000 miles per second, light is fast by any human standard. But cosmic distances make even light seem slow. The nearest star is 4.2 light-years away. The nearest large galaxy is 2.5 million light-years away. The most distant galaxies we can observe are over 13 billion light-years away. If we wanted to send a message to a civilization in one of those distant galaxies, assuming one exists and could receive our transmission, we would have to wait over 13 billion years for our message to arrive, and another 13 billion years for any response to come back. The round-trip communication time would be longer than the current age of the universe. This means that any civilizations that might exist in the far reaches of the cosmos are effectively isolated from us. We can observe their galaxies, see the light from their stars, but we cannot communicate with them in any meaningful way. By the time our message arrived, their civilization might have risen and fallen countless times. The universe they inhabit when they receive our signal would be billions of years older than the universe we inhabit when we send it. This cosmic isolation is built into the structure of space-time itself, a consequence of the finite speed of light and the vast distances involved. Even within our own galaxy, distances are prohibitive. The Milky Way contains hundreds of billions of stars, and current estimates suggest that most of them have planets. Many of those planets lie within the habitable zones of their stars, the region where temperatures might allow liquid water to exist on the surface. If even a small fraction of those planets developed life, and a small fraction of those developed intelligent life, there could be thousands or millions of civilizations within the Milky Way alone. Yet, the distances between stars are so great that we have not detected any signals from them, and they presumably have not detected any from us. The Fermi paradox asks why, if the universe is so vast and contains so many stars and planets, we have not yet found evidence of other civilizations. Various answers have been proposed. Perhaps intelligent life is far rarer than we think, arising only once in billions or trillions of planets. Perhaps civilizations tend to destroy themselves shortly after developing advanced technology. Perhaps they are out there, but choose not to communicate, or use communication methods we have not yet discovered. Perhaps the distances are simply too great, and civilizations exist but remain forever isolated by the sheer scale of space. Or perhaps we are among the first intelligent species to arise, living in a young universe that will one day be teeming with life, but has not yet had time to produce many civilizations. We do not know the answer, but the question itself is shaped by the vastness of the universe. If space were smaller, if stars were closer together, if galaxies were more compact, the universe would be a very different place. Communication might be easier. Travel between stars might be feasible. Civilizations might encounter each other regularly, forming networks and alliances across space. But in the universe we actually inhabit, the scales are so enormous that isolation is the default condition. Each world is an island, each civilization a solitary voice calling out into the dark, hoping for, but not expecting an answer. The largest stars in the universe are unimaginably massive. Stephenson 2-18, one of the largest known stars, has a radius approximately 2,150 times that of the Sun. If placed at the center of our solar system, its outer layers would extend beyond the orbit of Saturn, engulfing Mercury, Venus, Earth, Mars, Jupiter, and Saturn itself. The star is so large that light takes several hours just to travel from one side to the other. Despite its enormous size, Stephenson 2-18 is relatively cool for a star, glowing a deep red color. It is a hypergiant nearing the end of its life, having already fused lighter elements into heavier ones in its core. Soon, on cosmic timescales, it will collapse and likely explode as a supernova, scattering its outer layers into space and leaving behind a dense remnant. At the other extreme are the smallest stars, red dwarfs that are barely massive enough to sustain nuclear fusion in their cores. These stars can be as small as 8% the mass of the Sun, glowing faintly in the red and infrared. They are so dim that not a single red dwarf is visible to the naked eye from Earth, even though they make up about 70% of all stars in the galaxy. Red dwarfs burn their fuel so slowly that they can shine for trillions of years, far longer than the current age of the universe. The universe is still too young for any red dwarf to have run out of fuel and ceased shining. Every red dwarf that has ever formed is still burning today, and will continue to burn long after larger stars like the Sun have exhausted their reserves and faded away. Neutron stars represent another extreme of cosmic density. When a massive star explodes as a supernova, its core can collapse into a sphere only about 12 miles across, yet containing more mass than the Sun. The matter is compressed to such incredible density that protons and electrons merge into neutrons, creating a substance unlike anything found on Earth. A teaspoon of neutron star material would weigh about 1 billion tons. The gravity at the surface of a neutron star is so strong that if you could somehow stand there, you would weigh billions of times more than you do on Earth, and you would be instantly crushed into a layer of atoms, just one atom thick on the star's surface. Some neutron stars spin extremely rapidly, rotating hundreds of times per second, their surfaces moving at a significant fraction of the speed of light. These rapidly rotating neutron stars, called pulsars, emit beams of radiation from their magnetic poles. As the star rotates, these beams sweep across space like the beam from a lighthouse. If the beam happens to point toward Earth during part of the rotation, we detect a pulse of radio waves or light, repeating with extraordinary regularity. Some pulsars keep time more accurately than atomic clocks, their rotation rates stable to within millionths of a second over years or decades. White dwarfs, the remnants of stars like the Sun, are less extreme but still remarkable. When the Sun runs out of hydrogen fuel in its core, about 5 billion years from now, it will expand into a red giant, swelling to hundreds of times its current size and engulfing the inner planets. Eventually, it will shed its outer layers, leaving behind a hot, dense core about the size of Earth, but containing more than half the mass of the original star. This white dwarf will shine not from fusion, but from stored heat, gradually cooling over billions of years until it becomes a cold, dark cinder floating through space. Most of the mass of the Sun, accumulated over 4.6 billion years, will end up locked in this small, dense sphere, slowly radiating its energy into the void. The oldest stars in the universe, formed when the cosmos was only a few 100 million years old, are still shining today. These ancient stars contain very few heavy elements, because they formed before multiple generations of stars had lived and spread their enriched material into space. Studying these old stars gives us a glimpse of what the early universe was like, before planets could form, before complex chemistry was possible. These stars are surviving relics from an earlier epoch, time capsules that have traveled through 13 billion years of cosmic history relatively unchanged. Globular clusters, dense spheres containing hundreds of thousands or even millions of stars, often harbor these ancient populations. The stars in globular clusters are bound together by gravity, orbiting a common center in a dense ball that can be tens or hundreds of light years across. Within a globular cluster, stars are packed much more closely than they are in the disk of the galaxy. If Earth orbited a star in the center of a globular cluster, the night sky would be spectacular, filled with hundreds or thousands of stars, bright enough to cast shadows, creating a sky that never truly became dark. Star clusters come in various sizes and ages. Open clusters are loose groups of stars, typically containing a few hundred to a few thousand members, born from the same molecular cloud and still traveling through space together. Over time, the gravitational influence of passing stars and gas clouds can disrupt open clusters, scattering their members across the galaxy. Most open clusters dissolve within a few 100 million years. Globular clusters, being much denser and more massive, can remain intact for the entire lifetime of the galaxy, tens of billions of years or more. Our galaxy contains about 150 known globular clusters, each one a miniature city of stars orbiting through the galactic halo. These clusters are not confined to the flat disk where most stars reside, but instead follow elongated orbits that take them far above and below the galactic plane. When a globular cluster passes through the disk, it moves through a region of space that is, by its standards, quite crowded, increasing the chances of interactions with disk stars or clouds of gas. Most of the time, however, globular clusters travel through the relatively empty space of the halo, isolated islands of light separated by tens of thousands of light years from one another. The Milky Way's central bulge, a roughly spherical region at the galaxy's core, contains billions of older stars packed into a relatively small volume. The density of stars in the bulge is much higher than in the disk, where the Sun resides. If Earth orbited a star in the bulge, the night sky would contain millions of stars visible to the naked eye, compared to the few thousand we can see from Earth's actual location. The sky would glow softly, even without the moon, illuminated by the combined light of countless distant suns. Astronomers in such a location would have mapped the nearby stars long before developing telescopes, because so many would be visible and bright enough to study carefully. At the very center of the Milky Way, hidden behind thick clouds of dust that block visible light, lies Sagittarius A star, the supermassive black hole around which the entire galaxy rotates. This black hole contains approximately 4 million times the mass of the Sun, compressed into a region smaller than the orbit of Mercury. It sits there quietly, not actively feeding on large amounts of matter, occasionally flaring as a stray gas cloud or asteroid ventures too close and gets torn apart by tidal forces. Observations of stars orbiting very close to the galactic center have allowed astronomers to track their motions and confirm the presence of this massive object, even though the black hole itself emits no light. Stars very close to Sagittarius A star orbit at tremendous speeds, completing full orbits in just a few years. These stars experience extreme conditions, moving at several percent of the speed of light and passing within just a few light hours of the black hole's event horizon. The gravitational field is so strong that time dilation becomes significant. A clock on one of these stars would run noticeably slower than a clock farther from the black hole, a consequence of Einstein's general relativity. The stars themselves are mostly massive, bright stars, because smaller, dimmer stars would be difficult to detect against the glare of the crowded galactic center. Over time, some of these stars will likely venture too close, crossing the event horizon and disappearing into the black hole, adding their mass to the central object. Supermassive black holes appear to exist at the centers of most large galaxies, their masses ranging from millions to billions of times the mass of the Sun. The relationship between a galaxy's mass and the mass of its central black hole suggests that the two grow together, co-evolving over cosmic time. How these black holes form is still a subject of research. They might start as smaller black holes that merge and grow through accretion, or they might form directly from the collapse of massive gas clouds in the early universe. Either way, by the time galaxies reach maturity, most contain a central supermassive black hole that influences the surrounding region through its gravity and the energy released by infalling matter. Quasars, some of the brightest objects in the universe, are powered by supermassive black holes actively feeding on large amounts of gas. As matter spirals into the black hole, it forms an accretion disk that heats to millions of degrees, emitting more light than the entire galaxy surrounding it. Some quasars are so luminous, they can be detected from billions of light-years away, their light outshining trillions of stars. Most quasars are found in the distant universe, corresponding to times when the cosmos was younger and black holes were more actively feeding. In the modern universe, most supermassive black holes are relatively quiet, having consumed most of the gas in their immediate vicinity. The farthest galaxies ever observed are seen as they were more than 13 billion years ago, appearing to us as small, irregular collections of young stars still in the process of formation. These early galaxies are much smaller than modern ones like the Milky Way, containing perhaps only a few billion stars compared to hundreds of billions today. Over cosmic time, these small galaxies merged and grew, building larger structures through countless collisions. The process is ongoing. Even today, the Milky Way is in the process of absorbing several smaller satellite galaxies. Streams of stars from these disrupted galaxies spread across the sky, gradually joining the larger structure. Galaxy collisions are spectacular but slow. When two galaxies merge, their stars pass through each other like two clouds of gnats, very rarely colliding because the distances between individual stars are so vast compared to their sizes. But the gravitational interaction distorts both galaxies, pulling out long tidal tails of stars and gas, triggering bursts of star formation where gas clouds collide and collapse. Over hundreds of millions of years, the two galaxies spiral around each other, losing energy to gravitational radiation and dynamical friction, until they finally merge into a single, larger structure. The resulting galaxy is often elliptical rather than spiral, its orderly rotation disrupted by the chaotic encounter. Our own galaxy's merger with Andromeda, predicted to begin in about 4 billion years, will unfold over a similar timescale. The first close passage will send ripples through both galaxies, disrupting spiral arms and flinging some stars into intergalactic space. The supermassive black holes at the centers of both galaxies will eventually spiral together, merging into a single, more massive black hole. The Sun and its planets, if they still exist, will likely survive the merger unscathed, because the probability of a direct collision with another star is vanishingly small. But our neighborhood in the galaxy will change. Stars from Andromeda will mix with stars from the Milky Way, creating a new combined galaxy that astronomers have nicknamed Milkomeda. The night sky from Earth, if Earth still exists and has an atmosphere, will look very different, filled with new stars and stripped of the familiar Milky Way band. The universe on the larger scales appears to be homogeneous and isotropic, meaning it looks roughly the same in all directions and at all locations, at least when averaged over sufficiently large volumes. This is known as the cosmological principle, and it simplifies our models of the universe enormously. If the universe had a preferred direction or a special location, we would need much more complicated theories to describe it. But observations confirm that on scales of hundreds of millions of light-years or larger, the distribution of galaxies is statistically uniform. There is no cosmic center, no edge, no direction that is fundamentally different from any other. This uniformity extends even to the cosmic microwave background radiation, the faint glow left over from the Big Bang. This radiation fills all of space, coming from every direction with nearly equal intensity. The temperature variations across the sky are tiny, only about 1 part in 100,000. Yet these tiny variations encode information about the early universe. Regions that were slightly denser than average eventually became the seeds of galaxies and galaxy clusters, their gravity pulling in surrounding matter and growing over billions of years into the structures we see today. The pattern of temperature variations in the cosmic microwave background acts like a cosmic blueprint, showing where future galaxies would form long before the first stars ignited. The fact that we can observe the cosmic microwave background at all is remarkable. This radiation has been traveling through space for nearly 13.8 billion years, crossing almost the entire observable universe to reach us. Along the way, it has been stretched by the expansion of space, shifting from visible and infrared light into the microwave portion of the spectrum. Every cubic centimeter of space is filled with about 400 photons of this radiation, remnants of the hot, dense early universe, now cooled to just a few degrees above absolute zero. These photons are all around us, passing through our bodies constantly, mostly unnoticed except by specialized instruments designed to detect them. The temperature of the cosmic microwave background, about 2.7 Kelvin, tells us something important about the universe. It is much colder than it was when the radiation was first released, when the temperature was about 3000 Kelvin. The cooling has occurred because of the expansion of space, which stretches light to longer wavelengths and lower energies. By measuring the current temperature and comparing it to the temperature at emission, we can calculate how much the universe has expanded since that time. The answer is roughly a factor of 1000, meaning the universe is about 1000 times larger now than it was when the cosmic microwave background was emitted. Yet here we are, watching anyway. We build telescopes and satellites, we develop theories and equations, we peer into the depths of space and try to make sense of what we see. This is a remarkable thing, that matter organized into human form should care about the nature of the cosmos, should spend time and resources trying to understand distant galaxies and ancient photons. There is no survival advantage to knowing the diameter of the observable universe or the number of galaxies it contains. These are not things that help us find food or avoid predators. They are luxuries, the products of minds that have solved the immediate problems of survival and now turn their attention to questions of curiosity and wonder. The expansion of the universe is not an explosion into empty space, but rather space itself growing larger. This is a subtle but important distinction. When we say galaxies are moving away from us, we do not mean they are traveling through space in the conventional sense. Rather, the space between us and them is stretching, carrying the galaxies along with it. Imagine a loaf of raisin bread in an oven. As the dough rises, the raisins move away from each other, not because they are traveling through the dough, but because the dough itself is expanding. From the perspective of any single raisin, all the other raisins appear to be moving away, and the farther away a raisin is, the faster it seems to recede. This is what we observe in the universe, every galaxy moving away from every other galaxy, with more distant galaxies receding faster. This expansion was discovered in the early 20th century by Edwin Hubble, who measured the distances and velocities of nearby galaxies and found a direct relationship between the two. Galaxies that are twice as far away are moving away twice as fast. Galaxies 3 times as far are moving 3 times as fast. This relationship, known as Hubble's law, implies that the universe is expanding uniformly in all directions. It also implies that if we run the expansion backward in time, all the galaxies converge toward a single point, suggesting that the universe began in an extremely dense, hot state about 13.8 billion years ago. This is the Big Bang, not an explosion in space, but an expansion of space itself from an initial state of extreme density and temperature. The Big Bang was not an event that happened at a particular location in space. It happened everywhere at once. Every point in space, including the spot where you are sitting right now, was part of the initial dense state. The expansion has been carrying these points apart ever since, and it continues today. In this sense, we are still inside the Big Bang, living in a universe that is still expanding from its initial moment of creation. The expansion rate is slowing down due to gravity, which pulls galaxies together. But recent observations suggest that the expansion is actually accelerating, driven by the mysterious dark energy that pervades all of space. Dark energy is perhaps the deepest mystery in modern cosmology. It appears to make up about 68% of the total energy content of the universe. Yet, we have no idea what it is. Its effects are observable through the accelerating expansion, and its properties can be measured, but its fundamental nature remains unknown. Various theories have been proposed, from modifications to Einstein's equations to exotic new fields permeating space, but none has been confirmed. We know dark energy is there because we can see its effects, but we do not yet understand why it exists or what gives rise to it. Future observations from ground-based telescopes and space missions may provide clues, but for now it remains one of the great unsolved problems in physics. The composition of the universe is surprising when broken down by percentages. Ordinary matter, the stuff that makes up stars, planets, and us, accounts for only about 5% of the total mass energy. Dark matter, the invisible substance that holds galaxies together, makes up about 27%. The remaining 68% is dark energy, causing the expansion to accelerate. This means that everything we can see and touch, all the stars and galaxies and nebulae, all the planets and moons and asteroids, all the atoms in our bodies, represent less than 5% of what the universe contains. The rest is hidden from us, detectable only through its gravitational and expansive effects. This realization has profound implications. It means that our understanding of the universe is incomplete in a very fundamental way. We are studying a minority component of reality, and the majority remains mysterious. This is not unusual in the history of science. Previous generations thought the Earth was the center of the universe, then learned it was just one planet among others. They thought the Sun was the center, then learned it was one star among billions. They thought the Milky Way was the entire universe, then learned it was one galaxy among trillions. Each expansion of our cosmic perspective has revealed that what we previously thought was everything was actually just a small part of a much larger whole. The discovery of dark matter and dark energy is another step in this progression, another humbling reminder that the universe is larger and stranger than we imagine. Gravitational waves, ripples in the fabric of space-time itself, offer a new way to observe the universe. Predicted by Einstein's theory of general relativity and directly detected for the first time in 2015, gravitational waves are produced by accelerating masses, particularly extremely dense objects like black holes and neutron stars. When two black holes spiral together and merge, they create powerful gravitational waves that spread outward at the speed of light, slightly stretching and squeezing space as they pass. These waves can be detected by extraordinarily sensitive instruments that measure changes in distance smaller than the width of an atomic nucleus. The detection of gravitational waves opened a new window on the universe. For most of history, astronomy has been done with light, observing the electromagnetic radiation emitted by stars, galaxies, and other objects. Gravitational waves provide complementary information, revealing events that produce little or no light but generate significant distortions in space-time. The mergers of black holes, for instance, can now be observed through gravitational waves, even though the merging black holes themselves emit no light. This has allowed astronomers to study black hole populations, measure their masses and spins, and test Einstein's theory in strong gravitational fields. Neutron star mergers, which do produce light in addition to gravitational waves, have been observed through multi-messenger astronomy, combining gravitational wave data with electromagnetic observations. These events are thought to be the source of many heavy elements, including gold and platinum. When two neutron stars collide, they release enormous amounts of energy, synthesizing heavy atomic nuclei that could not form inside stars. The debris from these collisions is ejected into space, enriching the interstellar medium with elements that eventually find their way into new stars and planets. The gold in wedding rings, the silver in jewelry, the platinum in catalytic converters, all likely formed in neutron star mergers billions of years ago, scattered into space and eventually incorporated into the material that formed the Sun and Earth. The scale of energy released in these cosmic events is difficult to comprehend. A supernova, the explosion of a massive star, releases more energy in a few seconds than the Sun will emit over its entire 10 billion-year lifetime. For a brief moment, a supernova can outshine an entire galaxy, visible across millions or billions of light years. The explosion ejects the star's outer layers into space at speeds of tens of thousands of miles per second, creating an expanding shell of gas and dust that can remain visible for thousands of years. The Crab Nebula, the remnant of a supernova observed by Chinese astronomers in the year 1054, is still expanding today, nearly 1,000 years later, and will continue to expand and fade for thousands more years before eventually dissipating into the interstellar medium. Gamma-ray bursts, the most energetic explosions in the universe since the Big Bang, release as much energy in a few seconds as the Sun will emit over its entire lifetime, but focused into narrow beams that can be detected from halfway across the observable universe. These bursts are thought to occur when extremely massive stars collapse directly into black holes, or when two neutron stars merge. The beams of gamma rays, if pointed toward Earth, can be detected by satellites, appearing as brief, intense flashes, lasting anywhere from milliseconds to several minutes. The total energy output, integrated over all directions, is almost incomprehensible. For a few moments, a gamma-ray burst outshines everything else in the universe, a beacon visible across billions of light years. Fortunately, gamma-ray bursts are rare, and the beams are narrow. so the chances of Earth being hit by one are very small. If a burst occurred within our galaxy, and the beam happened to point toward us, it could potentially strip away part of Earth's atmosphere and cause mass extinctions. Some scientists have speculated that past mass extinctions might have been triggered by nearby gamma-ray bursts, though there is no direct evidence for this. Most bursts occur in distant galaxies, far enough away that by the time the gamma rays reach Earth, they have spread out and weakened to levels that, while detectable, are not dangerous to life on the surface. The chemistry of the universe has evolved over time. In the first few minutes after the Big Bang, when the universe was still extremely hot and dense, nuclear reactions occurred that produced mostly hydrogen and helium, with trace amounts of lithium. Everything heavier than lithium was formed later, inside stars. The first stars to form, composed almost entirely of hydrogen and helium, were likely very massive and short-lived, burning through their fuel quickly and exploding as supernovae, scattering the first heavy elements into space. Subsequent generations of stars formed from gas enriched by these heavy elements, and they in turn produced more, gradually increasing the abundance of carbon, oxygen, iron, and other elements. By the time the Sun formed, about 4.6 billion years ago, the material from which it condensed contained about 2% heavy elements, enough to form rocky planets like Earth. Without those heavy elements, Earth could not exist, nor could life as we know it. Carbon is the backbone of organic molecules. Oxygen is essential for water and respiration. Iron is crucial for hemoglobin and many proteins. All of these elements were forged inside stars that lived and perished before the Sun was born. We are made of recycled stardust, atoms that have been through multiple stellar generations, each cycle adding more complexity to the cosmic mix. The age of the universe, 13.8 billion years, has been determined through multiple independent methods, all of which converge on similar values. Measurements of the cosmic microwave background radiation provide the most precise estimate, because the detailed pattern of temperature variations encodes information about the age, composition, and geometry of the universe. Observations of the oldest stars, whose ages can be estimated from their luminosity and chemical composition, provide another constraint. The expansion rate of the universe, measured through observations of distant galaxies, provides a third. All of these methods agree that the universe is approximately 13.8 billion years old, with an uncertainty of only about 1%. This age sets a scale for cosmic time. 13.8 billion years is the entire history of everything, from the initial moment of expansion to the present. It is the time available for galaxies to form, for stars to ignite and evolve, for planets to coalesce and life to arise. On one hand, it is an enormous span of time, longer than human minds can fully grasp. On the other hand, it is finite, and there are processes that would require even longer timescales. The universe has not yet existed long enough for the smallest red dwarf stars to run out of fuel. It has not existed long enough for all the black holes to evaporate through Hawking radiation. There are structures and phenomena that have not yet had time to emerge, waiting for future epochs when the universe is older still. Looking forward, the ultimate fate of the universe depends on the nature of dark energy. If dark energy remains constant, the expansion will continue to accelerate forever, eventually carrying all but the nearest galaxies beyond the cosmic horizon. In the far future, countless trillions of years from now, galaxies will be isolated, surrounded by empty darkness, as all other galaxies have receded beyond the observable limit. Stars will continue to form from remaining gas, but eventually the gas will be exhausted and no new stars will be born. Existing stars will age and fade. White dwarfs will cool into black dwarfs. neutron stars will radiate away their heat, and black holes will slowly evaporate through quantum effects. After an almost unimaginable span of time, much longer than the current age of the universe, even the black holes will disappear, leaving a cold, dark, empty cosmos with nothing but scattered particles and faint radiation. This far future is called the heat decline of the universe, a state of maximum entropy where no useful work can be done and no complex structures can persist. It is a somber vision, a universe that has run down like a clock, all its energy spread out and diluted until nothing interesting remains. But this is trillions upon trillions of years away, a timescale so long that it makes the current age of the universe seem like the blink of an eye. For now, the universe is young, vibrant, full of stars and galaxies and light. There is no need to worry about its ultimate fate. We are living in a fortunate epoch, a time when the cosmos is rich with structure and complexity, when the night sky is filled with galaxies, and the questions we ask have answers we can discover. The vastness of the universe invites a sense of perspective. When we contemplate the scale of space and time, our everyday concerns seem smaller, less overwhelming. The argument that upset you yesterday, the mistake you made at work, the worry that keeps you awake at night. All of these are real and valid within the context of your life, but they are also temporary and local. The universe has existed for 13.8 billion years. It will continue for trillions more. In the grand sweep of cosmic history, this moment is brief, and your troubles are not permanent. This is not meant to diminish your experiences or invalidate your feelings. Rather, it is a reminder that there is a larger context, a broader perspective, and that sometimes stepping back to see the bigger picture can provide relief from the intensity of immediate concerns. At the same time, the vastness of the universe makes the fact of our existence all the more precious. In all the observable cosmos, as far as we know, Earth is the only world that hosts life. We might not be alone. There may be countless other worlds with their own biospheres scattered across the galaxies. But we have not yet found them. For now, we are unique, the only part of the universe that can observe and understand itself. This is both humbling and empowering. It means that what happens here matters, at least to us. The choices we make, the things we create, the knowledge we gain, all of this is significant, because there is no one else, as far as we know, doing the same thing. We are the universe's consciousness, its capacity for wonder and beauty and understanding, made manifest in biological form. Life on Earth is part of an unbroken chain that stretches back 4 billion years to the first simple organisms that arose in the oceans of the young planet. Those early life forms were nothing like modern cells, likely just clusters of molecules capable of self-replication, competing for resources in a world without oxygen or complex chemistry. Over billions of years, through countless generations and countless evolutionary innovations, life grew more complex. Single-celled organisms gave rise to multicellular ones. Simple body plans evolved into elaborate structures. Eventually, nervous systems developed, and with them, the capacity for perception, memory, and thought. The human brain, with its 86 billion neurons and trillions of connections, is one of the most complex structures in the known universe. A network of biological computing power that can contemplate its own existence and ponder the nature of the cosmos. This complexity arose not through design, but through the blind workings of evolution. Natural selection operating over immense timescales to gradually build structures that are well adapted to their environments. The eye, for instance, seems too complicated to have arisen by chance. But it evolved gradually, starting from light-sensitive cells and slowly refining over millions of years into the sophisticated organ we have today. Each small improvement provided a survival advantage, allowing organisms with better vision to outcompete those with worse vision, passing on their genes to the next generation. Multiply this process across countless generations and countless lineages, and the result is the diversity of life we see today. From bacteria to blue whales, from fungi to redwood trees, all connected by descent from common ancestors, all part of a single family tree that spans the history of life on Earth. The fact that life exists at all is remarkable. The universe is not particularly hospitable to living things. Most of space is cold, dark, and empty. Most planets are uninhabitable, too hot or too cold, lacking water or air or stable surfaces. Even Earth, the most hospitable place we know, has experienced multiple mass extinctions, events where large fractions of all species vanished in geologically short periods of time. Life persists not because the universe is friendly, but because it is resilient, adaptable, capable of thriving in a wide range of conditions and recovering from disasters that would seem fatal. Yet, for all its resilience, life is also fragile. It requires specific conditions to flourish: liquid water, a source of energy, a supply of nutrients, a stable environment. Remove any of these, and life struggles. Earth provides all of them, maintained by a complex interplay of geological, atmospheric, and biological processes. The atmosphere keeps the surface warm enough for liquid water, shields harmful radiation, and provides the oxygen and carbon dioxide that many organisms need. The magnetic field deflects solar wind that would otherwise strip away the atmosphere. The moon stabilizes Earth's axial tilt, preventing wild climate swings. The sun provides a steady source of energy, shining reliably for billions of years. All of these factors together make Earth a sanctuary for life, a rare oasis in the vast desert of space. Other planets in our solar system might host life, or might have in the past. Mars likely had liquid water on its surface billions of years ago, when its atmosphere was thicker and its climate warmer. Life might have arisen there, and if it did, it might still exist in protected niches underground, where liquid water might persist. The moons of Jupiter and Saturn, particularly Europa and Enceladus, have subsurface oceans beneath their icy shells, kept liquid by tidal heating from their parent planets. These oceans might provide habitats for life, isolated from the surface but supplied with energy and nutrients from hydrothermal vents on the ocean floors. We do not yet know if life exists in these places, but they are among the most promising locations to search within our solar system. Beyond our solar system, the search for life focuses on exoplanets, planets orbiting other stars. Thousands of exoplanets have been discovered, ranging from gas giants larger than Jupiter to rocky worlds smaller than Earth. Some orbit within the habitable zones of their stars, the region where temperatures might allow liquid water on the surface. These planets are targets for future observations, where astronomers will use advanced telescopes to study their atmospheres, looking for chemical signatures that might indicate the presence of life. Oxygen, for instance, is highly reactive and would quickly disappear from an atmosphere unless continuously replenished by biological processes like photosynthesis. Detecting oxygen in the atmosphere of an exoplanet would not prove the existence of life, but it would be strong evidence worthy of further investigation. The search for extraterrestrial intelligence, through efforts like SETI, looks for signs of technological civilizations by scanning the sky for radio signals or other emissions that could be artificial. So far, no confirmed signals have been detected, but the search continues. The absence of evidence is not evidence of absence. The universe is vast, and we have searched only a tiny fraction of it. Civilizations might exist, but use communication methods we have not yet discovered. Or they might be too far away for their signals to reach us. Or they might have already risen and fallen long before we arrived on the scene. The search for life, whether simple or intelligent, is one of the great quests of our time. A question that speaks to our place in the universe and our desire to know if we are alone. Whether or not we find life elsewhere, the knowledge we gain from studying the cosmos enriches our understanding of nature and our appreciation for the complexity and beauty of the universe. Every galaxy imaged, every exoplanet discovered, every gravitational wave detected adds to our picture of reality. This knowledge is not just abstract or academic. It has practical applications, from improving technology to inspiring future generations of scientists and explorers. But beyond its utility, knowledge for its own sake has value. There is joy in understanding, satisfaction in solving puzzles, wonder in discovering that the universe is even more intricate and magnificent than we imagined. The images captured by space telescopes showing galaxies billions of light years away, or nebulae glowing with the light of newborn stars, are among the most beautiful creations of science. They reveal a universe that is not cold and sterile, but colorful, dynamic, filled with structure and change. Star-forming regions glow red and pink from ionized hydrogen. Planetary nebulae shine in greens and blues as dying stars shed their outer layers. Galaxies show sweeping spiral arms traced out by bright young stars. These images are not just scientific data, they are works of art, expressions of the cosmos's capacity for beauty. They remind us that the universe is not just something to analyze and measure, but something to appreciate and celebrate. In a very real sense, we are the universe looking at itself. The atoms that make up your body were forged in stars billions of years ago. They have cycled through multiple generations of stellar birth and collapse, scattered into space and gathered back into new stars and planets. Some of the atoms in your hand right now might have been part of a different star system before our Sun and Earth formed. They have traveled across light years of space, assembled and reassembled countless times, and now they are part of you, arranged in a pattern complex enough to think and wonder about its own origins. You are not separate from the universe. You are a piece of it, a temporary configuration of matter that has somehow achieved consciousness. This perspective can be both humbling and empowering. It is humbling because it reminds us how small we are in the grand scheme of things, how brief our lives compared to the age of the cosmos. But it is empowering because it shows us that we are not outside or apart from nature. We are nature, as much a part of the universe as stars or galaxies or black holes. The same forces that govern the motion of planets govern the motion of our bodies. The same atoms that make up distant nebulae make up our cells. We are connected to everything, part of an unbroken chain that stretches back to the Big Bang and forward into an unknown future. As you lie here tonight, drifting towards sleep, let your mind wander through the vastness we have explored together. Picture the Earth, a small blue sphere hanging in space, surrounded by the thin atmosphere that shields us from the void. Zoom out and see the Moon orbiting nearby. Then the other planets of the solar system, each one a world with its own characteristics and mysteries. Pull back farther and watch the sun shrink to a point of light among many others. the stars of the Milky Way spreading out in every direction. See the galaxy itself, a spiral of light and darkness slowly rotating through space. Pull back even more and watch the Milky Way become just one galaxy among many, part of a local group, part of a supercluster, part of a vast cosmic web that fills all of observable space. And then stop. Rest here, in the darkness between galaxies, where the light of stars is faint and far away. Feel the silence, the stillness, the immense patience of space itself. Nothing here rushes. Nothing demands your attention. The universe simply is, vast and calm and eternal. Let that vastness hold you. Let it remind you that your worries are small and temporary, that the cosmos has room for everything, that there is no hurry, no urgency, no need to do anything but rest. The universe is still expanding. Stars are still shining. Galaxies are still slowly wheeling through space. All of this will continue whether you are awake or asleep, whether you are thinking about it or not. The cosmos does not need you to hold it together. It will take care of itself. You can let go. You can close your eyes and drift, knowing that you are part of something far larger and more enduring than any single moment of worry or stress. Tomorrow, the sun will rise again, just as it has every day for 4.5 billion years. The earth will turn, the moon will orbit, the stars will shine. The universe will continue its slow, majestic unfolding, indifferent to our individual concerns, but providing the stage on which all of life plays out. You are safe here, on this small world, in this quiet corner of an enormous galaxy, in a universe so large it defies comprehension. You are small, yes, but you are also here, alive, aware, part of the ongoing story of the cosmos. Let the vastness of space be a comfort rather than a source of anxiety. Let it remind you that there is always more, always room to grow, always new things to discover. The universe is full of possibilities, full of places we have never seen and might never see, full of phenomena we are only beginning to understand. It is a place of wonder, and you are part of it. So breathe deeply. Let your muscles relax. Let your mind slow down. The universe is patient. It has waited 13.8 billion years. It can wait a little longer while you rest. There is no urgency, no deadline, no requirement that you understand everything tonight. The stars will still be there tomorrow, and the questions will still be worth asking. For now, just rest. You have done enough for today. You have thought about the universe, considered its size, marveled at its beauty. That is enough. Now it is time to let go, to release your grip on wakefulness, and to drift into the quiet darkness of sleep. Close your eyes. Feel the weight of your body sinking into the surface beneath you. Let your breathing slow and deepen. Let your thoughts grow quieter, more distant, until they fade into the background like stars disappearing into the dawn. The universe will continue without you for a few hours. The galaxies will keep spinning, the stars will keep shining, the cosmos will keep expanding. And when you wake, it will all still be here, vast and mysterious and beautiful, waiting for you to wonder about it again. But for now, rest, sleep, dream of other skies, other worlds, other possibilities. Let the enormity of space cradle you in its infinite patience. Good night.